So in this last session of the AFLOW school, I'm going to talk a bit about how we can use, so we've shown already in all the previous talks how we can generate data in sort of a high throughput automated fashion, how we also have built up a large library of materials, data that's stored in sort of an organized way that can be accessed through an API. And now we want to show what kind of things we can do when we have these kind of big data repositories. And for this, so one of the things that you can do with these kind of large databases, and probably the thing that's now sort of the current, currently in vogue, is to train machine learning models. So, like I said, I've shown how tools like this REST API and AFLOW, we can have a way to wrangle data. These entries, the properties for all of these entries were calculated with DFT, which requires high performance computing environment. And even with this, so calculations can take days to even to months for some calculations, like Marco was mentioning the AAPL calculations for lattice thermal conductivity, can take, these are huge calculations. So we want to use the existing data that we've managed to build up inside our databases to construct models that can predict these types of properties, but without much less lower computational expense. So you can almost do on the fly determination of materials properties. So here's one example. So this is what we call this PLMF machine learning model that was trained on AFLOW data. So we took, basically there's two parts to this model. First, we took data for something like 26,674 materials. So these are materials that were in the ICSD part of the database. So these are things that are known to exist. So these are things that are already being observed experimentally, for which we've calculated properties. So there was about 26,000 of these that were calculated where we had things like the electronic band gap or band structure information or energetic information. And there was maybe about another 3,000 of these. There was a subset, maybe about 3,000 at the time, that had thermal and mechanical properties that were calculated with AEL and AGL, which are the methods that I went through this morning. So the predictions are based on structural morphology and elemental properties. So the way it works is that for each atom in the lattice, you create what's called a Voronoi cell around that atom. So what you do is you basically set it for each pair of atoms, like these two pairs, you draw a plane half at the midpoint between the two atoms. So then you surround each atom by a set of these planes with all the neighboring atoms. And then what we do is we look at the Voronoi cell of this atom and the neighbors, and if any two the Voronoi cells for any two atoms share a face like this, then these two atoms are considered to be bonded. So in this way, you can basically connect the atoms together to form something like a crystal graph. So this is what we mean here, that this Voronoi tessellation, so this is dividing up the space, is used to determine the atomic connectivity. And then we connect the ones that share a Voronoi cell face to form a crystal graph. So then these connected atoms, they form what we call structure fragments descriptors. So we have the nodes are the atoms, nodes of this graph, then the edges are these bonds. Then we have these path fragments. You can have linear fragments, circular fragments, etc. So we build up these fragments and these form the feature vector for the machine learning model. And then we decorate the nodes, so these atoms, with elemental properties. So things like the number of valence electrons, ionization potential, electron affinity, electronegativity, and so on. And this is what we call these property labeled materials fragments. So PLMF, and that's where the name of this model comes from. So these property labeled materials fragments, these then form the feature vector that's used to train the machine learning model. So in this case, we use a method called gradient, our collaborators used a method called gradient boosting decision trees. And so they trained these decision trees on these models, on this data, on these property labeled material fragments feature vectors. So models look something like this. So first of all, you have the electronic properties model. So first, there's a classification model to predict whether the material is a metal or an insulator. If it's predicted to be an insulator, if it's predicted to be a metal, then there's no band gap. If it's predicted to be an insulator, then you predict the band gap using a regression model. And so this gives you then the electronic band gap. Then we also do on a subset of these materials for which we have the thermomechanical properties available. We do, we train regression models, so things like bulk modulus, shear modulus, the Debye temperature, and so on. So then just to show you some analysis for the kind of things this model predicts. So to see how it's actually working, what kind of features it's using to predict the different properties. So here, for example, on the left, we see a bulk modulus. So this is the change in the standard, basically the change in the bulk modulus from the average against the atomic volume. And you can see that as the atomic volume goes up, the bulk modulus goes down. So this is more or less what you expect. So because if atoms are closer together, it's going to be, the material is generally stiffer for shorter bonds. And this is something that's reasonably well known in the literature, that bulk modulus has an inverse dependence on the volume per atom. On the right, we see something that's a bit stranger. It's something we don't really understand yet, and it might well be an artifact of the training data. But you can see that the Debye temperature seems to be a strong dependence of the Debye temperature on the anisotropy of the crystal cell. So B and C are the lengths of the two different cell vectors. So you can see that the more that if you have one vector here, if the C vector is much larger than the A vector, then you tend to have higher Debye temperatures. And we're still trying to understand why this is, where this is coming from. Then you can also see how useful the model is, how well it actually agrees with both the training data, which is density functional theory data, but also with experimental data that we can extract from the literature. So this is for a subset of the values. So we have the bulk modulus, the shear modulus, and the Debye temperature. So you can see that the bulk modulus, so here we have, on this axis, we have the experimental bulk modulus. So this is what's extracted from the literature. This is the calculated bulk modulus. So this we calculate with AEL, which I showed you in a previous session. And this is what was actually used as the training data. And finally, on this axis, we have the predictions that were given by the machine learning model. And you can see that all three are clustered quite close together, so they all agree quite well. Same thing for the shear modulus and for the Debye temperatures. There's a bit more spread in the Debye temperature, and you can see that the R-squared value is a little bit lower. So this is basically the R here is the Pearson correlation. So if this is equal to 1, then it would be a perfectly straight line. So it's a measure of how far away it is from linearity. Okay, so now these models that we've trained, we've also made them available online at the aflow.org website. So if you go here to the AFLOW-ML web application, so in the apps and docs section of the AFLOW page, then you will see these different machine learning models. So here's the PLMF model, which I've actually presented and discussed in detail. And there's also two other models that we have, which I'm not really going to explain how they work, but you can try them out and you can use them. So this is what's called, the next one is what's called a molar fragment descriptor model. So in this case, instead of training the model on including the crystal structure data like we did for the PLMF, so this model only includes chemical information. So that's why it's called molar fragment descriptor. So it's literally only the chemical formula. And again, it predicts similar properties. So you can see here, it predicts vibrational free energies and entropies of a crystal. And then finally, the last one. So this is for predicting superconductors. And this was, again, this was trained on experimental superconducting critical temperatures that were extracted from the literature. So then what you can do is you can copy and paste the postcard into this input section. And then you can click on run prediction. Now, there's something to mention about this postcard, and I'll go through this on a little bit later. So this is a bit different from the postcards we've been generating so far, because this is what's called a VASP5. So version 5.5 of VASP and up. There's a small difference in the postcards, and I'll go into this later from the ones for version 4 and below, which are the ones we were generating before with AFLOW. And then you can click here to run the prediction. And then you will get this prediction, which is, so this one is for magnesium oxide. So you can see this on an insulator with a band gap of, it's predicted to have a band gap of 3.37 electron volts. You can see the bulk modulus, shear modulus, heat capacity per cell and atom, constant pressure and constant volume, Debye temperature, thermal expansion, etc. So I said before that it's important to note that there's a difference between the version of the postcard that we were generating before with AFLOW, with the AFLOW proto command, and the version that we use for this machine learning model. And the main difference is that there's an extra line in this VASP5 version where we have a list of the chemical elements that we're using. So here, for example, I've shown sodium chloride as an example. So we can see that our two elements are chlorine and sodium. And here we had an extra line before this number of species. So just right after the lattice vectors, would again listed this element. So Cl and Na. So the reason for this is that in VASP, especially in VASP 4 and below, the VASP will determine the species being used from the potcar file. So this is the file with the pseudopotentials in it. And this is why it's so important to have these elements in the right order, because if you don't have them in the right order, because they need to be in the same order as they are in the potcar file, and the way AFLOW does it was it always does this alphabetically. So that's why it's so important to have these alphabetic. But if we're just uploading the postcard to a machine learning algorithm, we don't actually have the species information. So we don't actually have a potcar file, but we do need to tell it what elements we're using. So that's why we need to use version 5 and above, which has this extra line in it with a list of the elements. Okay. Okay, so here's some exercises. But before we go into these exercises, I'm actually just going to run through an example so we see online before we break up into the different breakout rooms. So I'll go here to, let me lower this. Okay, so if we go to aflow.org, if we go down to the bottom of the page, we can see the AFLOW-ML. And here we have our property labeled materials fragments. So here we have our place to put in our postcar file, and you can see it has this extra line with the species. So in the exercises, I say to use the Heusler structure that you decorated in the session 4. So there was the prototype session from VASP 4 to VASP 5. However, a lot of you might not be able to find this anymore. You might not have saved these structures. So I'm just going to, we can regenerate them. It's not, and it might be easier for this part at least to copy them directly from the AFLOW, from the Crystal prototypes page, rather than from the, trying to copy them from inside the portal, because it can be a bit tricky to copy things in and out from the portal. So we'll just do this again. We'll go here. We'll open up the Crystal prototypes page. We'll search for Heusler. And we find the right one. So this is the Heusler structure. So then I'm going to give you one example, and then you should go and try a different set of elements, any elements you like. So I'm going to do aluminum, nickel, and titanium. Then I'm going to create the VASP output. Okay, so here's our output file. So here's our postcar. This is a VASP 4 version of. So then we can copy. Come here. Place this file and paste it in. And then we go here. And we can add aluminum, nickel, titanium. And then we just hit run prediction. And we see we get the result. So we can see that this is a metal, so it doesn't have a band gap. You can see its bulk modulus, shear modulus, heat capacity, Debye temperature, thermal expansion. Okay. So I think with that, we can split up into our groups. So let me just run through quickly the exercises before we all go to the breakout rooms. So first one is to take this, to generate a POSCAR file. So you can use the online tool for this, and then convert it from a VASP4 version to a VASP5 version by adding this extra line. Then copy this structure into the AFLOW-ML application and run the PLMF model. Then do the same thing for the MFD model. And then for the ASC model, you don't need to do the POSCAR file. In this case, you just do a chemical formula. So you take whatever compound, whatever formula you use to decorate this, and then you upload it for the ASC model, and then find out what the superconducting critical temperature is. Okay, and with that, I think we can break up into our rooms, and let's allow about 10 minutes for this. So we'll meet back at 4:35 Central Time. Okay, so I've shown you, we did the exercise in the last session of how to do this manually. So you have an online interface, which is quite nice if you only have one material you want to look at. But if you wanted to have, if you want to be able to access the model programmatically, that means we wanted to build an application programming interface. So it's a bit like the same thing we did with the online, the web portal search functions versus the AFLOX API. So now we've also made our this machine learning web application. We've also built an API so that you can access it programmatically. So the way it works is you take your POSCAR. Again, this should be one for version 5 of VASP. You post the POSCAR to an endpoint. Then you get a response, which is like a task object, which includes a task ID. So then from this, you can then query another endpoint, which will include this task ID. And that will turn you another response, which will be a JSON file. Again, that will be either a status object, in which case it will tell you the success, whether the prediction has actually finished successfully or not. So if the success is no, if success is no, then it will, then you basically have to query it again until you actually get a success equals yes. Or sometimes you'll get a success as failure. Sometimes you get success. If it's pending, you can query again later. If it's a failure, that means something went wrong. So maybe your POSCAR wasn't formatted properly, for example. However, if it is successful, then you get back a prediction object, which will actually contain the values that you're looking for. So there's also, just wanted to mention here, in case you wanted to download, there's a machine learning client for this that you can download. But I'm not going to go into this in detail here because it gets a bit tricky to install. Plus, if you want to go through, there's some, if you can download this, there's some instructions and you can run it. I'll go through a bit later on as well. We also have a Jupyter notebook with instructions for installing these sort of things. So you can also look in there to try and get this to work, or you can send us an email. But we're not going to go into this here because it's a bit too time consuming to install. Okay, so here's an example of what the kind of things we were able to do with this AFLOW-ML API. So we integrated this PLMF model with a genetic algorithm code. So this code Extalopt, which is developed by our collaborators. So Professor Ava Zurich's group in University of Buffalo. So basically as SUNY Buffalo. And what we did was that with their genetic algorithm, it takes in, so you give it 2 different carbon structures. So a set of different carbon structures. It will then start combining these carbon structures to create new structures. And then it will calculate the energy, again with VASP. And then it will do another iteration whereby the structures with the lowest energy will again be combined, or let's say the highest fitness. And in this case, the fitness will be a combination of energy. So the ones with the lowest energy and also then the ones with the highest hardness. And to get the hardness, this is where we start using the machine learning application, because we want to be able to calculate elastic properties and use that in the machine learning model, then to calculate the hardness. So here we have a graph of some results. So here in the top left, these are the ones we're looking for. So they have both low energy and they have high hardness. And here, okay, I didn't include this in the slides, but just to mention the hardness we're using is what's called the Toher model for hardness, which basically is a model where they sort of were able to get this more or less empirically from the data that the hardness tends to depend on the shear modulus. So they have the model is basically that the hardness value is equal to 0.151 times the shear modulus. But you can read this paper here for more details. We tried a few of these different models. We found this Toher one, the one that just depends on the shear modulus, was actually the most robust for this particular application. And here's some different structures we found. In particular, this structure, which had a very high shear modulus, and when you could say, sorry, very high hardness. So this is a bit less than what's the experimental value, but when you take the actual value that's generated by our machine learning model, so it tends to underestimate the hardness somewhat. When you combine this machine learning model with this Toher model for hardness, you tend to get an underestimate. And so this is actually very similar to the kind of hardness you get from diamond. And what this structure is actually a combination of diamond and Lonsdaleite. So diamond is these blue, it's shown by this blue tiling. These are diamond-like structures. And then these other green and yellow ones are Lonsdaleite. So Lonsdaleite is like it's basically a hexagonal analog of diamond. And you can actually, if you look inside the prototype encyclopedia, you'll actually see Lonsdaleite inside as one of the prototypes. So you can actually look it up later if you like. Okay, so to show you how this API actually works. So here I mentioned before that you submit a postcard to an endpoint. So here's the actual endpoint. So it's http://AFLOW.org/API/AFLOW-ML/version v1.0. So this is version. Then PLMF. So this is the actual specific model we're looking for. If we want to do one of the other models, which we have also have MFD and the ASC models. So then we have /prediction, and then we use this -data-URL encode, and then we file at postcar. So this is our postcar file. So this one should be a version 5 version of the postcar. So then we retrieve a task object. So that's a JSON file with this ID. So this is the task ID. So this is the sort of a hexadecimal string. So then, and this gives you also some results endpoint. So then you query the task ID to retrieve the results. So again, we have the same server. So this time we leave out the model name because it's for a specific prediction. So we don't necessarily need to provide the model /result. And then we append this task ID. And then you receive this results object, which is again a JSON file, and it gives you different values. So again, the bulk modulus, shear modulus, the by temperature, heat capacity, and so on. And you can see also here we have the status part, which is success, and we also have the model, which is PLMF. And you'll notice here that we use essentially the same keywords with ML underscore appended to the front of them. So this is the so AEL underscore bulk modulus underscore VRH was what was used, was the AFLOW keyword, the values corresponding to this AFLOW keyword were used to train the model, and then the ML underscore shows that this corresponds to a machine learning prediction based on this and this keyword. Okay, so just to show how this works in practice and how this actually looks like, I'm going to go to the into the portal. So if we go again, so here we were at AFLOW day 3. If we now go into 10 machine learning, so this is the very last one. Then we go into AFLOW-ML API, do ls inside. Okay, let me remove this other postcard because this was one I generated earlier. Okay, so we have the script, we have then we have a postcard here. So if I do a cat, this is a postcard that should be inside your directory. So you can see this is a postcard for magnesium oxide, and you can see it has this extra line, NGO. So now we want to send this to the endpoint. So let me copy this. I should paste into the clipboard, hopefully. Okay, let me change this to .mgo. And then I can paste selection. Hopefully this will come up. And okay, so we see we ran this command, and then we get back. This is printed out to the screen. We get our task object. So this is a JSON object with the task ID. Okay, let me just open the chat to make sure I have everybody's, in case there's anybody. Okay, so now we want to query this task ID. So instead of trying to copy and paste on this thing again, I'm just going to edit the one I already had. So here we go with the prediction / result. And then we do our task ID. Let's see if this is in the clipboard. Yes. And then we edit paste selection. And it's not going to work because I need to add it in the slash. And now you see, we've retrieved our task object with things like the bulk modulus and the shear modulus and so on. Okay, but this can be quite tedious, typing these commands in by hand. So instead, I provided you, so the right thing to do is to automate this, so to build all this into a Python script. So let me go through this now. Okay, so so if you look inside, you can also look inside the directory. So let me open this first. So if you look inside, you'll see this AFLOW_ML API. So if we open this up, we'll see the script inside, so you can look inside. I'll just go through it on the PowerPoint so you can see more easily. Okay, so you can see we have various imports at the top. One important thing to note is that we import the sleep library. So this allows us to basically wait if the status object says that it's still pending, then we can sleep for 10 seconds and then try again. So this is the AFLOW-ML server. We're querying the PLMF model. We want to encode the postcar. So in this case, we want to say what the file name is. Then we retrieve the task object. So then, yeah, so we build our URL. We then request, we send the, basically upload our postcar. Then we retrieve our task object and we get the results endpoint. And then we build a results URL. And then we query this. So then we have this incomplete Boolean. And while this is still incomplete, it will continue to query the task object. So then it tries to request the results. It checks the status inside. If it's pending or started, it sleeps for 10 seconds. And so then it continues. So it basically goes back to the next thing in the loop. And so then an incomplete will still be true. But then if there's a failure, then it writes out an error message and it stops the loop. So incomplete now is false because it's complete. And if it's success, then it prints out the results. Okay. So now we have some exercises. So it says here to create the VASP to copy the VAS5 Heuser structure POSCAR, but we'll actually, I think it's easier to just actually use the command to make it again, and I'll go through how to do this before we go into the breakout rooms. And then modify the ML API script to print whether the material is a metal or an insulator, and if it's an insulator, to print the band gap. So then modify the script to run this MFD model. So in this case, you would swap the PLMF for MFD, and then print out the results and see what results are obtained, the results JSON. And then finally, this one's a little bit, it combines a few different things. So then you can use either AFLUX or the AFLOW.org advanced search page. It might be easier to use the search page to find the entry in the molybdenum titanium alloy system with the lowest formation enthalpy per atom. So if you're using the search page, I suggest you also click on lib2. So highlight lib2, and then download the relaxed structure. So you go inside the entry page, you find the relaxed POSCAR, so this concar relaxed 2, and copy it and convert it to VAS5 format, and then use the AFLOW-ML API to find the bulk and shear moduli for the structure. So this is a little bit more complicated. So before we go into the breakout rooms, let me just show you how to remind you again how to generate a POSCAR and convert it to VAS5 POSCAR. So I'll just run through the first one. So again, we have AFLOW -- proto equals, then we have T001.A to BC. And I'm going to use aluminum, nickel, titanium. So remember, it has to be in alphabetical order. Then I'm going to pipe it into a POSCAR. Okay, and because we're using this other style, not the ANRL style, we don't need to use the -- params command. Let's check if that works. Okay, so now we have a POSCAR. Go in, we can add the line. LNITI, save it. Now we can run. Okay, so now we have a successful prediction and it prints out all the different properties. Okay, I think with that we can go into our breakout rooms. I think because a few of these require a few different steps, let's meet back at 5:15 Central Time. Okay. Okay, we're just waiting for a couple more people to come back. I think everybody's starting to come back now. So just for the last 10 minutes, let me share my screen again, and I'll run through just the solutions to the exercises. Okay, I think we have everybody now. Okay. Okay. So let me just bring up the slides. So the first exercise was to use this POSCAR. So I already more or less went through this, but I'll just show you the last part of the script. So here we have this POSCAR file, we have a PLMF at the bottom. Then we read in this JSON object, and we read specifically, we check this particular entry in the JSON. So if the ML_EGAP_type is insulator, then you write the material is insulating and you write the band gap, which is this results_JSON ML_EGAP. Otherwise, we write out that the material is a metal. If the material is a metal, we write out material is metallic. Okay, so let me run this one. So here we see this postcard I generated was metallic. Okay. Then the next one was to use this MFD model, again send the same postcard and see what would happen if it what results it gave. So here we just print out the results. So really all we have to change here is this PLMF to MFD. And here it writes out the results. So you can see that it prints out the heat capacity at constant volume and the vibrational energy and the vibrational entropy. And then finally, the last thing was to find the structure with the lowest, structure in the molybdenum titanium binary alloy system with the lowest formation enthalpy. That's the first part. So here we do the search. We search for binaries. We're looking for molybdenum and titanium. Restrict this to 2. Then we go down to thermodynamics. Formation enthalpy per atom. Then we can do a restrict. And then we do a search. Now we want to sort. So we go up to the header of this column. And if you just hover over it, you can see it says sort by atomic formation enthalpy. Although you might not be able to see it, it's very small print. But if we click on this, then we get the lowest value at the top. So minus 160 millielectron volts per atom. So if we click on the API, we can scroll down until we see the list of files. And then we can click on this one, Concar Relax VASP. And we can copy this into our clipboard. Then we add line MO and TI. And then we can copy this into a Get a file and save it as a postcard. So here's our postcard. Version 5. And you can see I've saved it in the same directory as my scripts. So if I do postcard MO TI, you can see it's there with the extra line. Then if we look inside here, whoops. Here we should change this to do .MOTTI. And then we print out the bulk modulus and the shear modulus. So we save it. And then we can do Python, so we can run it. API 3. Let's see if it works. Okay, so here we go. Here's our bulk modulus and our shear modulus. Okay, so that basically brings us to the end of this last session. So I don't know if anybody has any other questions that they want to ask before we wrap up. Otherwise, I think Corey will want to say a few words at the very end. Just to clarify, just give some contact details if you have other questions and how to contact us, how to download AFLOW, these sort of details.